I'd like to thank Heather Douglas for the invitation to speak today and for all the work she has put into organizing this conference. Her lucid framing for the conference provides a definition of public engagement with science that emphasizes two-way communication. Indeed, public engagement is often distinguished from the public understanding of science in this respect as a commitment not just to informing the public, but to making science itself more responsive to public concerns. Public engagement in this sense is often traced back to the 1980s, when it's said to have emerged as a critique of the movement for a public understanding of science, which had set the narrow goal of translating science into a more user-friendly form. And the movement for public engagement, by contrast, acknowledged the declining legitimacy of scientific authority and envisioned a more participatory form of knowledge-making as the answer. Today, I want to explore with you another lineage for public engagement with science, one that may prove illuminating as an analog for today. This origin story will take us back to the aftermath of World War I in Central Europe. But let me begin by pointing out that we could tell many other histories of public engagement with a wide range of actors. One might focus, for instance, on popular epidemiology and the working class communities who have studied the toll of industrial pollution on their own health, on the outreach programs pioneered by the Black Panthers in the 1960s, or on the indigenous communities who have struggled to have their environmental expertise recognized and included in integrated assessments. In other words, theories of public engagement are indebted to members of the public who have taken engagement into their own hands. For today, though, I will approach the history of public engagement from the perspective of scholars who began to articulate this ideal in interwar Central Europe. I want to keep in mind, though, how much these scholars learned about the making of knowledge from the students, readers, editors, and other non-scientists with whom they engaged. In fact, these scholars built on a long tradition of practices of public engagement as a set of lived practices rather than a social and epistemological theory. The origins of public engagement lie in the pragmatic efforts to reform scientific language in order to make it easier for scientists to gather information from lay people. The goal of constructing a vernacular language for science dates back at least to the 18th century Swedish botanist Carl Linnaeus, who designed his taxonomic system in order to, quote, make botany easy for people without schooling or wealth. 19th century medical experts often eschewed Latinisms for the terms their patients used to describe their own experiences of illness. 19th century scientists also formulated wind scales and cloud taxonomies on the basis of the lingos of sailors and farmers. And they came up with terms for seismology that corresponded to the felt reports of earthquake victims. But in most cases, these efforts were largely pragmatic, reflecting the dependence of 19th century science on non-expert observers. And many scientists were grateful when mechanical detectors freed them from these ties to the public in the early 20th century. The 1920s, the period I'll focus on today, was the end of an era in this respect. In scientific fields ranging from seismology and climatology to botany and epidemiology, new laboratory methods, automated measuring and recording devices, and statistical techniques were rendering obsolete the painstaking work of collecting lay observations. Yet people could still remember a different time, a time when miners were fossil hunters and botanists consulted housewives on the uses of local plants, a time when the local meteorological station was run by an innkeeper or a clergyman, a time when newspapers solicited accounts from readers after every tumbler. Scientists were sensitive to the passing of these observational habits, and with them, the loss of a vital avenue of communication between experts and lay people. Those of you with backgrounds in sociology may associate the interwar period with the founding of the sociology of knowledge. Particularly influential for this field in the US was Robert Merton, who famously argued in the late 30s that democratic values such as disinterestedness and communalism are inherent to science. Left to its own devices, Merton argued, scientific communities would regulate themselves in democratic fashion. That may have sounded plausible from the perspective of a white male professor at Harvard. But intellectuals in Central Europe at the time had good reason to doubt it. Scientists and philosophers in Central Europe in the 1920s were witness to political and racial violence on a near daily basis, which threatened to destroy Central Europe's fragile new experiment with democracy. Unlike Merton, they could not afford to take for granted the association of science with democratic norms. I will focus today on 5 scholars who lived in 3 Central European cities, Vienna, Berlin, and Lviv. All 3 parts of empires that collapsed in World War I, the Austro-Hungarian for Lviv and Vienna, and the German Empire for Berlin. These monarchies had been discredited by the war's death tolls and the massive suffering on the home front. The war left behind economic devastation. University professors couldn't find food to eat in Vienna in 1919, while paper money became virtually worthless in Germany in the early 20s. At the time of the signing of the peace treaties in Paris, political conditions in all the defeated countries, Germany, Austria, and Hungary, were outright revolutionary. And along the disputed Polish-Ukrainian border, formal peace was still years away. Sailors played a key role in the German Revolution of 1918, which actually began as a mutiny at the naval base at Kiel, where sailors elected Soviets and demanded abdication of the Kaiser. The Weimar Republic was the work of the German Social Democratic Party's moderate wing, their attempt to forestall the Marxists. But the revolutionary situation continued in Germany into 1919. The leftist Spartacist uprising of that month resulted in a crackdown by the Social Democratic government in which the Spartacist leaders, Karl Liebknecht and Rosa Luxemburg, were murdered, further discrediting the new state. In Hungary, by comparison, a Soviet-style republic wrested power from the new liberal regime, only to be overthrown with the help of Western powers and succeeded by a brutal right-wing white terror. And the former Habsburg city of Lemberg, now Ukrainian Lviv, was caught up in ongoing warfare between the new states of Poland and Western Ukraine. From 1923, it was officially part of the Polish Republic, another state polarized between the political left and right, where an exclusionary anti-Semitic nationalism was on the rise. So when the post-war insurgencies and civil wars finally settled down, these 3 cities were parts of 3 new states, the republics of Austria, Germany, and Poland, each of them new to democracy, states whose legitimacy was disputed from the start. What's more, when war had broken out in 1914, much of the younger generation of Europeans had welcomed it, embracing the spirit of militarism. Those who didn't perish in battle went on to form a vital core of the fascist movements of the 1920s. They intensified their critique of timid bourgeois values and remained enthralled to the violence and authoritarianism of war. To sum up then, people were questioning not only the legitimacy of the new democratic governments, they questioned democracy itself as an ideal. The Great War was also a turning point for public views of science. Throughout Europe, the war had empowered scientific experts as never before. It's been called the chemists' war, for the strategic significance of newly synthesized lethal gases. Likewise, the introduction of airplanes to warfare called on physicists' knowledge of atmospheric dynamics, and economic experts found themselves in charge of planning wartime economies. And yet the mass slaughter enabled by new technologies simultaneously cast a shadow over the sciences, calling into question Europeans' long-standing equation of science with civilization. Meanwhile, the revolutionary new theories of relativity and quantum physics drew widespread curiosity among lay people, but suggested that physics was in a state of crisis. Quantum theory attributed behavior to particles that seemed downright mystical. The German author Oswald Spengler drew a wide following with his argument that quantum theory was a sign of the decline of the West. Through the 1920s, Vienna and Berlin remained islands of radical leftist politics, hence the moniker Red Vienna, even as conservative parties gained ground outside the metropoles. Since the turn of the century, both cities had served as incubators of cultural reform movements, including widely imitated programs of public housing, healthcare, and adult education for the working classes. Just as Vienna and Berlin, along with Lviv, had been centers of aesthetic modernism. But in the 1920s, these cities also became sites of right-wing and anti-Semitic activism, and political clashes were frequent, especially at universities. The University of Vienna, in particular, became a bastion of reaction in the 1920s. Well before the Austro-fascists came to power in 1934, students and scholars took it into their own hands to purge the university of Jews and socialists. The German Students' Association, a nationalist anti-Semitic fraternity, tried to intimidate Jewish students, while the university's rector blamed the resulting violence not on the perpetrators, but on the rapid growth in the number of Jews studying at the university. In fact, one theology professor publicly demanded a quota for Jewish students. At the time, the natural sciences departments were part of the philosophy faculty. In order to become eligible to become a professor, candidates had to defend a second dissertation. Conspicuously, in the cases of several Jewish and left-wing students, the philosophy faculty rejected the second dissertation, claiming that in one way or another it fell short of scholarly standards. Thanks to recent detective work in the archives by Klaus Taschner, we now know that these rejections were engineered by a secret group of right-wing anti-Semitic conspirators who called themselves the Bear's Lair and who held their meetings in the university's laboratory of paleontology. Thanks to Taschner's research, it's much clearer now just how powerful the forces of reaction were at the University of Vienna in the 1920s, well before the emergence in Germany in the early 30s of a movement for Aryan physics. Here's a scene from May 1925 of police, quote unquote, defending the University of Vienna. What had happened was that the murder of a social democrat in a working class neighborhood had led left-wing students to attempt a protest, which right-wing students took as an excuse to unleash mayhem. Violence in these years was directed above all against Professor Julius Tandler, director of the First Anatomical Institute at Vienna, a social democrat and Jewish by birth. Riots took place regularly at his lab between 1920 and 1933, when the injuries sustained by 20 students finally convinced Tandler to resign. Such was academic life in Central Europe in the 1920s. It is hard to imagine that any social theorist working under these conditions would have concluded, as Merton did, that science was necessarily a democratic force. Nor would it seem plausible that science could remain insulated from its social context. On the contrary, by 1930, several scientists and philosophers in these three metropolitan centers were articulating the vital importance of interactions between scientists and the public. All five of these men are well known to historians, yet no one to my knowledge has remarked on the coincidence that all five promoted the value of public engagement with science in the late 20s and early 30s, and often in similar terms. Remarkably, they share this common ground despite disagreements about epistemology, metaphysics, and politics. Consider, for instance, that Neurath and Fleck are often taken to represent diametrically opposed philosophies of science. Neurath is seen as a positivist who believed that science has the potential to be independent of the observer if only observations can be reduced to their most basic universal forms. While Fleck is seen as an anti-positivist who saw science as determined by its social context, by the character of what he called the thought collective. Politically, Neurath, Zilsel, and Benjamin were socialists, while Schrödinger was a moderate liberal, likewise probably Fleck. And yet, nearly simultaneously, each of these individuals began to call for two-way communication between scientists and the public. What explains this convergence? Ultimately, I will argue, these men were united by being witness to the co-opting of science and technology by the forces of political reaction. None of them could ignore the evidence around them that science bent to its social context. Moreover, even if they couldn't agree on a single political line, they shared a common set of enemies, fascists and their frequent bedfellows in those years, clerical conservatives. So let's turn to how these men thought about public engagement. A common move among them was to draw a distinction between two approaches to science popularization. Indeed, Schrödinger, Neurath, and Benjamin each spoke literally of two forms of popularization. Schrödinger grew up in Vienna, the son of an industrialist, and interestingly, he is the only one among these five without a Jewish parent. He had a dazzling career in physics, culminating in the Nobel Prize of 1933 for his contributions to atomic theory. In a piece for a general scientific audience in 1929, Schrödinger announced, there are two types of popularizers. The first lowers himself to the level of the reader from his lofty heights of expertise. The other raises the reader and himself into a more general sphere that lies above that of technical expertise. Those of the first type feign sympathy with the less educated, but use jargon and mathematical formulas as crutches and grow cranky without them. Those of the second type take pleasure and pride in freeing themselves from such crutches. Schrödinger insisted repeatedly in the late 20s that this second mode of popularization benefited science as well as the public. What happens, he asks, when a specialist must explain to a layman why he studies what he does? Schrödinger answered, you, the specialist, will try to defend the reason why you are interested, and you will become aware of the fact that only now, in your discussion with your colleague, have you reached those aspects of the subject that are, so to speak, nearest your heart. Elsewhere, Schrödinger wrote that if a scientist found it difficult to explain his ideas to a layperson, then he hadn't clearly grasped those ideas himself. Schrödinger followed these prescriptions in his own work. He criticized his colleagues for being satisfied with descriptions of the atomic world that could not be squared with common sense. His best-known contributions to physics, the formulation of quantum physics known as wave mechanics, was the fruit of his efforts to make the new physics of the atom visualizable. Walter Benjamin was born to a middle-class Jewish family in Berlin in 1892. He stands out in the company of these scientifically trained men because he was a philosopher and literary critic without training in the natural sciences. For him, the immediate impulse to rethink popularization came from a new technology of communication, the radio. In the late 1920s, German radio carried a popular scientific broadcast roughly once a week. Benjamin saw in radio the potential for a shift toward a more democratic form of science, science in the broad German sense of both the natural and the human sciences. Benjamin followed his friend, the playwright Bertolt Brecht, in insisting that radio be used as a medium for the production of knowledge, not merely its diffusion. As Brecht put it, the radio would be the finest possible communication apparatus in public life if it knew how to receive as well as to transmit, how to let the listener speak as well as to hear, how to bring him into a relationship instead of isolating him, kind of like Zoom, I suppose. To Benjamin, radio seemed to, quote, demand a complete transformation and reclassification of the subject matter from a popular perspective. In 1932, in an essay entitled Two Forms of Popularization, Benjamin envisioned a form of radio that would demonstrate to the listener, quote, that his own interest is of substantive value to the subject, that his questions, even if not spoken into the microphone, pose new questions for scientific research. In other words, science would benefit right along with members of the public. Here he wrote, it is a matter of a popularization that not only brings science closer to the public, but also brings the public closer to science. In short, a truly popular orientation is constantly active. It has a direct, transformative impact on science and scientific knowledge. According to Benjamin, not every science could achieve the second, truly popular orientation. The discipline ripest for it, he believed, was physics, with its revolutionary new theories of relativity and quantum mechanics. Schrödinger would surely have agreed. At such a moment of radical creativity, it was possible for scientists to make their audience feel a part of the process of innovation. Benjamin hinted that only in such revolutionary periods did scientists have the humility to admit uncertainty about the future course of their research. Only at such a moment of upheaval might public engagement wield any real influence on science itself. Otto Neurath was born in Vienna to a Jewish father who was an academic and a Catholic mother. From his early studies of philosophy, math, and physics, Neurath later turned to economics and ultimately the philosophy of science. He too drew a contrast between two ways of approaching popularization. In its usual sense, popularization referred to attempts to simplify complex ideas for the public. A second form of popularization, or what Neurath called humanization, moved in the opposite direction. It was the effort to, quote, begin our explanations in accordance with the knowledge and vocabulary already familiar to the people. He elaborated, one should try to build up more comprehensive knowledge by simply looking at the environment and by using the language of daily life and its derivatives. In the mid-1920s, Neurath introduced his picture language, or isotype, as a means of humanizing science by providing a commonly understood, unambiguous visual vocabulary from which more complex ideas could gradually be constructed. For Neurath, the goal of communicating science was not to force-feed knowledge to non-experts. It was to carve out a space where scientists would be compelled continually to revise and refine their descriptions of the world in accordance with the widest possible range of experiences, in part by making the languages of different disciplines mutually comprehensible and as congruent as possible with the languages of everyday life. One of Neurath's interlocutors in Vienna was Edgar Zilsel. Zilsel was born in Vienna, the son of a lawyer. He studied philosophy, math, and physics in Vienna. As a Jew and a Marxist, his chances at an academic career were slim. Indeed, his second dissertation on the history of the concept of genius was rejected by the philosophy faculty, ostensibly due to its unconventional methodology. In fact, Zilsel fell victim to the bear's lair. Zilsel nonetheless forged ahead with his research, and his work proved path-breaking for the history of science. In his account, modern science only became possible once scholars gave up their disdain for manual labor. Historically, the scientific method originated with craftspeople. Having outgrown the constraints of guild tradition and being stimulated to inventions by economic competition, they were no doubt the real pioneers of empirical observation, experimentation, and causal research. The epochal shift from the scholasticism of the medieval universities to the empiricism of Vesalius, Bacon, and their successors depended then on breaking down the class barrier that divided learned men from menial laborers. Zilsel began to lecture on this theme in Vienna in 1930, though he was not able to publish it until 1932. His key point was that modern science began when scholars began to talk to craftspeople. Science began with public engagement. Ludwig Fleck grew up in a middle-class Jewish family in Lviv, then Lemberg, and trained as a physician and bacteriologist. He began publishing on the sociology of science in 1927. He's best known today for his concept of the thought collective, which he defined as a group of people mutually exchanging ideas. For Fleck, cognition was a collective process. Fleck's choice of the German word Kollektiv was deliberate. It was a rejection of Gemeinschaft, the German word for community, with its increasingly exclusionary and anti-modern connotations. Indeed, a German critic charged in 1936 that Fleck's use of the word collective hinted at Soviet sympathies. In Fleck's view, the problem with science lay with those thought communities, note his choice of word, that showed intolerance towards outsiders. Such exclusionary communities often wrongfully dismissed legitimate research problems as unworthy of their consideration. In Fleck's vision for science, an individual could move freely between thought collectives, belonging to more than one at once, thus becoming a vehicle for what he called intercollective communication. As Fleck envisioned the social landscape of knowledge, there was an expansive intersection between the spheres of science and of everyday life. Communication kept this a porous boundary. So one could always locate, quote, items of popular knowledge from other fields within the depths of these sciences. Fleck thought of everyday reality and common sense as the soil nourishing all specialized spheres of thought. He wrote, so-called common sense, as the personification of the thought collective of everyday life, has become in this way a universal benefactor for many specific thought collectives. And independently of Zilsel, Fleck traced the historical origin of modern science to the everyday sphere in which a variety of ordinary human activities converged. Surely, he wrote, there had always existed thinking typical of the natural sciences. It was to be found among the artisans, the seamen, the barber surgeons, the leather workers and saddlers, the gardeners, and probably also among children playing. Wherever serious or playful work was done by many, where common or opposite interests met repeatedly, this uniquely democratic way of thinking was indispensable. By democratic, Fleck meant here a form of knowledge that both resulted from and served a free and open confrontation among different points of view. He argued that scientific knowledge was robust precisely because it was not the product of a single individual, but rather democratically constructed by a mass collective. In short, his claim was that, quote, natural science is the art of shaping a democratic reality and being guided by it, thus being reshaped by it. Fundamental to Fleck's concept of science, then, was a reflexivity or capacity for self-correction. In a striking, memorable metaphor, he likened the work of science to that of a river cutting its own bed. What did he mean? The energy of a flowing river changes the water's own course, but energy is also lost through friction with the riverbed. To complete the metaphor, Fleck must have had a notion of the source of this resistance to the course of science. What was the terrain into which the river had to carve itself? It was, I would suggest, the common ground of everyday reality. Communication with the public provided the friction necessary to keep the scientific river on course. I hope that I've been able to convey the similarities in the ways these five thinkers thought about the value of interactions between scientists and the public. Now the question is, how can we explain the emergence of a shared ideal of public engagement there and then? First, we might attribute this convergence to the inspiration provided by a regional hero, Ernst Mach, a physicist who taught for 30 years in Prague before becoming the first professor of history and theory of natural science in Vienna. The philosophical club known as the Vienna Circle, which both Neurath and Zilsel frequented, grew out of a group that initially called itself the Ernst Mach Society. Mach studied physics and psychology, and he conducted research at the intersection between the two. He's best known, though, as a philosopher of science, a positivist. He sought to rid science of any trace of metaphysics. Science should concern itself only with what could be directly observed. In the context of his day, this denunciation of metaphysics was a strike against the authority of the Catholic Church in Austria. Mach portrayed science as an evolutionary process, stemming from practical engagement with tools. Everyday knowledge and physical instinct were essential ingredients in science. He devoted a great deal of energy to writing user-friendly textbooks and to promoting education for girls and the working classes. Although he never explicitly argued for the value of public engagement for the sciences, he did insist that scientific language needed to be held to a standard of universal intelligibility. The aim of science was not to explain, but to describe reality, and to do so as economically as possible. Was Mach the model for the ideal of public engagement that emerged in the 1920s? Certainly, Neurath and Schrödinger echoed Mach when they argued that communicating with the public would purify and universalize scientific language. Zilsel channeled Mach when he theorized the origins of modern science in the knowledge of craftspeople. However, Benjamin and Fleck referenced Mach not at all. Another possibility is that the shared ideal of public engagement grew out of shared experiences of interacting with non-scientists. Indeed, even as scientists' reliance on lay observers was dying out circa 1920, another set of practices of public engagement was gaining ground in both Vienna and Berlin, adult education courses. Here you see an image of the Urania Observatory, which was one of a large number of sites for adult education in Vienna from the early 20th century. The Vienna Circle's manifesto of 1929 referred to the spirit of enlightenment manifest in Vienna's scientifically oriented people's education. And Neurath and Zilsel regularly taught such courses on a variety of topics in science and philosophy. Closely associated with the adult education movement was a pioneering model for museum-based education in Vienna, the Social and Economic Museum, which Neurath founded in 1924, drawing on his theories of visual education and his isotype pictorial language. Yet the influence of the adult education movement is directly evident only in the lives of Neurath and Zilsel. Ultimately, a remarkable thing about these five men is how little they had in common. True, most were born into Jewish families in the German or Austrian Empire in the 1880s or 90s, and each followed closely the revolutions in physics of the first 2 decades of the 20th century. But otherwise, they shared little common ground. They occupied a broad philosophical spectrum between realism and idealism, as well as a political spectrum between moderate liberal and Marxist. Nor were they joined in their subsequent fates. Schrödinger found refuge from the Nazis in Dublin, where he lived well as the director of an institute for theoretical physics. Fleck remained in Lviv through the German invasion. He survived internment in Auschwitz and then Buchenwald only because the Nazis recognized his medical expertise. But his fortunes turned after the war, and he found a successful career as a bacteriologist, first in Poland and then in Israel. Neurath escaped to England in 1940, and after 8 months in an internment camp, he was able to relaunch an academic career at Oxford. He passed away there 5 years later. The other two were not so fortunate. Both Benjamin and Zilsel died by their own hands. Benjamin in 1940, seeing no escape from German-occupied France. Zilsel in California in 1944, after 5 lonely years as a refugee in the US. To conclude, each of these 5 men made a daring move in the context of their times when they underlined the need for two-way communication between scientists and the public. They argued that public engagement benefited science itself in 2 ways. The first was not necessarily controversial. Communication with non-scientists could free science of technical jargon and elucidate its murkier concepts. Their more radical intervention was to suggest that science would benefit from humility on the part of researchers, a willingness to relinquish some of their intellectual autonomy, even potentially to allow the public to redirect the course of research. This move is all the more surprising if we consider that at the very same time, scientists in the US were honing the ideology of pure science, effectively a bid to shield themselves and their work from public scrutiny. Given that these 5 individuals did not see eye to eye on politics nor on epistemology, we can only conclude that they were driven to this radical proposition by the one experience they did share, witnessing firsthand the dangerous turns that science took in Central Europe even before the Nazis came to power, from the use of chemistry and physics to facilitate mass slaughter in wartime, to the exclusion of Jews and socialists from university posts in the 1920s. From their perspectives, it sure did not look like democratic values came naturally to scientific communities. Although they never went so far as to phrase it this way themselves, we might say that these scholars saw public engagement as the best and only hope to reorient science's ethical compass. Almost immediately, events proved them wrong. The 1930s saw the launch of the Nazis' T4 program, as well as of the Tuskegee syphilis study. These events taught the lesson that science needs explicit codes of ethics and review boards to enforce them. But these men were not all wrong. Science also needs scientists who listen attentively and with humility to the public's concerns. Thank you.